Welcome back to Math 111. This is part 2 of Chapter 7 on basic probability. In part 1, we introduced the basic concepts of probability and random variables. We focused on discrete random variables in particular. In part 2, we will be discussing expectation, standard deviation, and a special type of discrete random variable called a binomial random variable. Always remember to make sure the Mosaic and TigerStats packages are loaded prior to starting your work. And let's get started with expectation. Recall that a random variable is a variable whose value is the outcome of an experiment. A random variable can take on any value in its range of possible values. However, there are some values that might be more probable than others. In other words, there are values of the random variable that are more expected than others. This is the idea behind the expected value. The expected value is the value of a random variable that we would expect to see if we repeated the experiment many times. It's sort of like the average of the possible values of a random variable, but it's weighted according to the likelihood of each of the values. The formula for expected value is shown here by this summation. To compute it, we would multiply every value in the range of the random variable by its corresponding probability, and then we would sum up these products. Let's look at an example. So you probably remember this example from part 1 of the chapter 7 slides. The experiment is tossing one fair coin 2 times. So the random variable x is defined to be the number of heads. And recall we said that x could take on the value 0, no heads, 1, where one head is tossed, or 2, where both tosses result in a head. And we saw that x equal 1 was more likely than x equals 0 or x equal 2. So the most likely value of x is 1. This should give us some idea of what we expect x to be. Let's compute it. Here we've listed all possible values that x can assume, along with the corresponding probabilities. We did this in the last set of slides, so if you don't remember, you might want to flip back to part 1 of chapter 7 and review this. To compute expected value, we multiply each value of x by its probability. So we would take the value 0 times the probability that x is 0.25. And we would add that to the next value that x can assume, 1, multiplied by the probability that x is 1, and so on and so forth. So the expected value of the random variable x is 1. Not terribly surprising based on our analysis in the previous slide. We've also included the R code to compute this in RStudio. So let's talk about this for a second. There are 3 objects defined here. Little x corresponds to the range of the random variable x. So it's a list. We use the concatenate function when we make a list, and the values in the list are the possible values that the random variable can assume. Prob.x is another list. Here we're using concatenate again, and the list this time is the corresponding probabilities. It's important that the order of these 2 lists coincide. So since the object x was defined in the order 0, 1, 2, the probabilities must be listed in the corresponding order, 0.25, 0.5, 0.25. The last object that's defined is ev.x. This is the formula here that computes the expected value. And the last line of code you see is just us calling the object ev.x to see the value, and we got 1. This chunk of code can be copied, pasted, and modified in the future for you to compute expected values for other random variables. Now, knowing the expected value is not quite enough to give us a true picture of a random variable. The standard deviation of a random variable is the same concept that we've encountered in the past with standard deviation. It is a measure of the give or take. In other words, it measures the amount that we would expect a random variable x to differ from its expected value. The formula is shown below here, along with a description of how you would go about calculating it. We won't spend a lot of time on this, but just really quickly, what's going on is we're taking the deviation of each value in the range of x from the expected value, squaring that deviation, and then weighting it by the likelihood that the random variable takes on that value. These products are summed, and then finally we take the square root of the sum. We can quickly do this in R, so let's go back to our example. So again, this is talking about the random variable that's defined to be the number of heads in 2 tosses of a fair coin. So here we've listed the range of the random variable x and the probabilities again, along with the expected value that we calculated a few slides ago. We first look at the deviations of each value of x from the expected value. So here's where you're getting the 0 minus expected value, 1 minus expected value, 2 minus expected value. These deviations are each squared, and then they're multiplied by the corresponding probability. So the 0.25 is placed here because it's the probability that corresponds with the value 0. 0.5 is placed here because it's the probability that corresponds to the value 1, and so on. We add this all up, take the square root, and we get the standard deviation is approximately equal to 0.7. It would be a good idea for you to flip back and forth between this slide and the previous one to help compare the formula with an application of it, so it will help you to understand the formula better. So as you can see, the formula done out by hand or on a calculator even can get a little bit cumbersome when you have a random variable that can take on a lot of different values. So R makes this computation much easier than doing it by hand or on a calculator. The first 3 lines of this code chunk should look familiar. They are the same lines that computed the expected value. Here's the list of the values of x. Here's the list of the probabilities. Remember, these 2 things need to correspond. Here's the line that computed the expected value. Since we're trying to compute standard deviation, I'm not going to call expected value. I'm just going to use it in the next line where I actually define sd.x as the standard deviation using the formula that you saw a couple slides back. And then we call sd.x to see the standard deviation, and we see that it's 0.7071. Again, this code chunk is a good one to copy and paste and modify to help you compute standard deviations of random variables in the future. Expected value and standard deviation work together to paint a picture of how a random variable is likely to turn out. So for example, suppose you have 2 options for a $100 bet. We will define the net gains for the 2 options as random variables. So let's let capital X be the net gain from making bet 1, and we'll let capital Y be the net gain from making bet 2. It would be useful to have an idea how each of these random variables might turn out in order to make the most educated bet. Here are the PDFs for the 2 different bets. Recall from the last set of slides that PDF stands for Probability Distribution Function. So this was just a way that we sort of organized the possible values that a random variable could assume along with their corresponding probabilities. So let's talk through the PDF for bet 1. The possible values for the random variable x are $5,000, $1,000, and $0. So keep this in context. If you place your money on bet 1, then the possible net gains that could occur are $5,000, $1,000, or $0. So you could win $5,000, $1,000, or nothing at all. You can then see the likelihood of each of these possibilities happening in the second row of the PDF. Now compare this information with the PDF for bet 2. If you place your money on bet 2, you could either win $20, $10, or $4, with the corresponding probabilities 30%, 20%, 50%. Which bet would you rather make? One way to evaluate this is to take a look at how much money you would expect to gain from each bet. In other words, compute the expected value. We'll do this in R. So you can see that the code from the previous slides has just been modified to fit each of these bets. In other words, we've just changed the values in the list of x and the corresponding probabilities for the expected value for the random variable x, and we get the expected value to be 10. Over here, we've changed a few things as well. We've changed the list of the values of y and the corresponding probabilities, and we get the expected value of the random variable y to also be 10. So it turns out that the expected gain from each bet is the same, $10. So we need more information. Let's take a look at the give or take, in other words, the standard deviation. How much can we expect the gain to differ from $10 by? Well, if we add in this one more line of code to compute the standard deviation, we see that the standard deviation for bet 1 is $172.90. So if we place our money on bet 1, we can expect to gain $10, give or take $172.90. While the expected gain is the same as bet 2, we can see that there's a lot of variability here. But let's wait and see how this compares to bet 2. The expected net gain for bet 2 was $10, but give or take $6.93. Now that you have a more clear picture of the money that you are likely to gain by making each of these bets, you can make a more informed decision about which bet you would like to make. What do you think? As promised, let's move on and talk about a special kind of discrete random variable called a binomial random variable. A binomial random variable counts how often an event occurs in a given number of tries of an experiment. There are four main characteristics of a binomial random variable. First, there are a specified number of tries. This is denoted by lowercase n. It's often referred to as the size. Second, each try results in either a success or a failure. Third, each try has the same probability of success. This probability is denoted by little p. Finally, the tries are independent of one another. In other words, the outcome of one try does not affect the outcome of another. Let's look back at our example of tossing a fair coin 2 times. If we let x be the number of heads, then x is a discrete random variable that is counting up the number of times an event occurs in a given number of tries. Since we are flipping the coin 2 times, the number of tries is 2, so the size, or little n, equals 2. Each flip results either in a head or a tail. Which one of these is considered a success depends on how the random variable is defined. Since the random variable is counting the number of heads, then we denote a success as flipping a head and a failure as flipping a tail. The probability of a success is 0.5, and this is the same on each flip. The tries, or the flips, are independent. In other words, the outcome of the second flip does not depend in any way on what happened on the first flip. So this is a binomial random variable with n equals 2 and p equals 0.5. Okay, so let's change this slightly. Let's suppose that we toss a fair coin 10 times now, and we'll let the random variable capital Y be the number of tails in 10 tosses of a fair coin. Okay, now the number of trials is 10 since we are tossing the coin 10 times, so n equals 10. There are still only 2 outcomes of this experiment. This time we denote a success as tossing tails because of what our random variable is counting, the number of tails. Then the failure would be tossing heads. As before, the probability of success is 1/2, and the tries are independent, so capital Y is a binomial random variable with n equal to 10 and p equal to 1/2. Let's try taking a look at a non-example. Let's let the random variable capital Z equal the number of children who will get the flu this winter in a kindergarten class with 20 kids. Capital Z is certainly a discrete random variable, and it's counting up the number of successes in a given number of children. So since there are 20 children, we can say that n equals 20, and classify a success as a child who gets the flu, and a failure as a child who stays healthy. So at first glance, this may appear to be a binomial random variable. However, the probability of a child getting the flu is unknown, and it's not constant. In other words, some children may be more likely to get sick than others. Also, children are not independent in this scenario because they're sharing a classroom. If one child gets the flu, this would raise the probability that other children will also get the flu. So the outcome of one child may affect the outcome of another. For those reasons, capital Z is not a binomial random variable. Probabilities associated with binomial random variables are really easy to compute in R using the p-binom GC function. So let's look at the random variable capital Y that we saw before, counting the number of heads in 10 tosses of a fair coin. This will help us to see how this function works. Let's start by computing a less than or equal to probability, such as the probability that capital Y is less than or equal to 3. Keep your thinking in context. This is the probability that you would toss 0, 1, 2, or 3 heads in 10 tosses of a fair coin. There are 4 inputs to the p-binom GC function, along with an option to output a graph of the PDF, similar to what you've been seeing in the slides up until this point. The first input is the bound, or the value of the random variable. Then you input what region you want to compute. This corresponds to the direction of the inequality that you are looking for. The size, or the value of n, comes next, and then the probability, and then finally you have the option to output a graph. It's a good idea to get in the habit of outputting a graph to make sure the correct bars are shaded. You'll understand this better as we look at more examples. So for this function, the default for region equals below is less than or equal to. So if you are looking for the probability that a random variable is less than or equal to some value, then that value is the value of the bound that you plug into the function. Let's take a look at the output. So the console will output the probability, and it will also appear as part of the histogram that's plotted. By looking at the shaded bars on the histogram, you can verify that you computed the probability that you intended to compute, the probability that y is less than or equal to 3, this left tail probability. Let's do some more. Suppose you want to compute a probability with a strict less than inequality, such as the probability that capital Y is less than 3. All of the inputs are the same as before, except the bound. If you input 3 as the bound here, you would compute the probability that we just computed, the less than or equal to. Since less than or equal to is the default for this function, we need to make a conversion. We need to convert y less than 3 to y less than or equal to 2. Since we are dealing with a discrete random variable, these expressions mean the same thing. Think about it. Y less than 3 means y is either 0, 1, or 2. Same thing, y less than or equal to 2 means y is either 0, 1, or 2. So we've converted the strict less than inequality to what the p-binom GC function interprets as the default. Keep in mind, outputting the graph helps to verify that we've computed the correct probability. So take a look. Notice that now only the bars strictly less than 3 are shaded. So remember, when you are wanting to compute left tail probabilities, in other words, below regions, the default for p-binom GC is to compute less than or equal to whatever bound you input. If you want strictly less than, you have to shift down a number. So let's turn this around now to right tail probabilities, strictly greater than and greater than or equal to. For a right tail probability, in other words, an above region, p-binom GC computes strictly greater than inequalities by default. This makes sense, since this is the opposite of a less than or equal to. So if we want to compute the probability that y is strictly greater than 3, our bound input will be 3. The region is above, and the size and probability are as before, since we are still doing the 10-coin toss. Let's take a look at the graph. All of the bars in the right tail, starting at 4, are shaded, so we did this correctly. The probability is 0.8281. If we had instead wanted to compute the probability that the random variable y is greater than or equal to 3, we need to convert greater than or equal to the default, strictly greater than. So greater than or equal to 3 is the same thing as strictly greater than 2. Everything else remains the same. Again, output the graph always to make sure that what you've computed is what you intended to compute. There we go. Greater than or equal to 3 shades the right tail starting at 3. So this probability is 0.9453. Now those are the basics, but you can do more with this function. Suppose we wanted to compute the probability that the random variable y is greater than or equal to 2, but less than or equal to 4. So we have two bounds this time, and we want the region between them. So the bound input is entered in as a list using the concatenate function, and the region is between. And there we go. Lastly, suppose you wanted to compute the probability that y exactly equals 4. Keep this in context again. This is the probability that a fair coin would land heads exactly 4 times when tossed 10 times. We can use the between value for the region argument again. This time, however, our list of bounds will be 4 and 4. This is like y is greater than or equal to 4 and less than or equal to 4, which is the same thing as saying y is exactly equal to 4. And we get only the bar over 4 shaded in. So this probability, the probability that you would toss exactly 4 heads in 10 tosses of a fair coin, is about 21%. Just a few last details about the binomial random variable. We talked earlier about computing expected value and standard deviation for a discrete random variable. Well, if we're dealing with a binomial random variable, we could compute expected value and standard deviations like we showed before. However, there are simpler formulas for expected value and standard deviation that you can use if you know you are dealing with a binomial random variable. We avoid all of the summation by using these. So the expected value of a binomial random variable is the size, n, times the probability, p. The standard deviation is the square root of n times p times 1 minus p. These are a lot easier than the formulas you saw earlier in this section. So let's compute these values for our 10 coin toss example. Remember, for this example, n is 10 because we're flipping a coin 10 times. Since it's a fair coin, the probability of it landing heads is 0.5. So the expected value of y is n times p, 10 times a half, which equals 5. This makes sense, right? If we toss a fair coin 10 times, we would expect to see it land heads half of the time, or 5 out of the 10 times. The standard deviation is about 1.581. Putting all of this together, we could say we would expect the value of the random variable to be 5, give or take about 1.58. This wraps up part 2 and our discussion of discrete random variables. In part 3, we will move on to continuous random variables. Thanks for watching.